welcome to this recording of advanced customizations in deep learning and neural networks. So, this is a master notebook of augmentations and generalization techniques. In this single notebook covers section A through K. I'll just quickly show the summary what we will do in sections A to K. So, yeah, so we have this section collab divided in k sections. So all the sections we are doing the same action with TensorFlow and one time with the PyTorch. So like section A is L1 L2 regularization, so we will do it once with TensorFlow and once with PyTorch. Similarly, B is dropout, once with TensorFlow, once with PyTorch. Early stopping, MC dropout, then wait initializations. All these functions, operations that we are performing, we are doing with both PyTorch and TensorFlow. So let's start with the code. So in the first cell, we are importing all the standard libraries, TensorFlow, Keras, PyTorch. We are setting the seed value to 42 so that it should be fair and reproducible, and that's all. In the second cell, we are loading our dataset. Our dataset is fashion MNIST dataset. It's built into Keras, and that's why we are using it. We will load the raw data in the Keras, and then we will normalize the pixel values. Once that is done, we will flatten the images to 784 dimensional vectors, and then we will carve out the validation set from the training data. So basically we have the training data, and we have 48,000 training data, out of which we will carve out 12,000 as validation, 10,000 as the test data, and we will also create a small training set to force overfitting. So we will set around 3,000 data for a small training set, and then once that is done, we will convert everything to PyTorch tensors also, so that we can use them during the PyTorch operations. And then we will wrap them in a PyTorch data loaders, and we will define the class names for readable plots later. And some sanity test we are doing, we are printing the sizes of the data sets and everything. So let's see. We can see this is the TensorFlow trend test split data set, and this is for the PyTorch. And let's move towards the section A, that is the L1 L2 regularization. We will do A/B test for almost all the sections. That is, we will do one with suppose for this section we will do it in three models, that is with no regularization, one with L2 regularization, and one with L1 regularization. We'll do same for 50 epochs, and here we are building a 3-layer dense model with optional regularization. And then we are building three models, one with no regularization, one with L2 regularization, and one with L1 regularization. And then we will combine all the three with same optimizers and losses, and then we will train all the three models using XTrain, that is the small data set, to force the overfitting. And then we will train the L2 regularization, and then we will train on the L1 regularization. Once all the models are trained, we will plot the training and validation accuracy for all the three models, and we will see the final scores. So this is the graph that we have plotted. This one, the red one is no regularization, blue is the L2 regularization, and the green is the L1 regularization. We can see the overfitting gap that is decreasing from no regularization to L2, and from L2 it again decreases to L1. So we can see the accuracy is also decreasing, the validation accuracy is also decreasing, and the overfitting gap is also decreasing. So everything is decreasing from no regularization to L2 and L1. Now let's see the same L2 and L1 regularization with PyTorch. So PyTorch doesn't have any inbuilt kernel regularization like Keras. So instead we will use L2 pass width decay to the optimizer, and for L1 we will manually add L1 penalty to the loss inside the training loop. So first we will define a simple 3-layer neural network. Then we will define a generic function for which we will do if L1 lambda is greater than 0, we will manually add the L1 penalty. And if L2 is handled by weight decay, then we will do weight decay in the optimizers. We'll see how we implement it. So this is our epoch phase. So in the training phase we are computing the loss, and here we are doing the annual penalty thing, and then we are optimizing it, and we are tracking it, and then we are doing the validation phase. So we will create the three models with different regularization, one with no regularization, one with L2 regularization, and one with L1 regularization. So we have created these three models. We will train all the three models now, and then we will plot the result, and we will see the summary. So with no regularization, it looks something like this. This is for the L2 and this is for the L1. You can see L1 and L2 look similar, almost similar, while the for the tensor flows there was a sudden visual difference we can see. Here the overfitting gap is almost same for L1 L2, while the accuracy of L2 is much better than the L1, and with the no regularization being the best, but the overfitting gap is still larger in the uh, no regularization graph. Moving forward to the next section is the dropout section. So first we will implement dropout with the TensorFlow. So dropout basically is randomly turning off the neurons during the training. This forces the network to rely on any single neuron and act as an ensemble for many smaller networks. We will again do A/B test here. Model A will be no dropout, model B will be dropout with 0.3, and model C with the dropout of 0.5. That is the standard and most common choice. So we have defined a build model, dropout model here, where the dropout rate default is 0, and dropout is placed after each hidden layer. So we will define this model here, and we have defined layer 1, layer 2, and then the output layer. We'll build again the three models as we have discussed with different dropout values, and then we will train all the three models, and we will plot the result, and we will see the final summary. So we can see with no dropout, with dropout 0.3, and with dropout 0.5, it almost overlapped. So we can see dropout lowers the training accuracy. So as we increase the dropout, the accuracy decreases, and the overfitting gap also decreases. So now we will implement the dropout with PyTorch. So in PyTorch, NN.dropout is the layer, just like in Keras. So model.train enables the dropout, and model.evaluate disables the dropout. Uh, Keras does this automatically, but PyTorch does not. So let's see how. We'll define the network with configurable dropout. We have given default as 0, and then we will also define the training functions for the same pattern. We will do the training for each epoch, then model dot evaluation, and then return the values. Now we will build and train the three models, and then we will plot the graph and print the summary. So again we are doing the same dropouts on the same data set, but with the Keras. So this is what we can see. There is again decrease in the accuracy, and decrease in the overfitting gap also. Next point is early stopping in TensorFlow. So training too long will give model. If we train a model too long, what will happen is the model will memorize the training data. That is the overfitting condition. So the solution is to stop the training automatically when the validation loss stops improving. So what we will do? We will define three models, one with the full 150 epochs, one with the early stopping patience is equals to 5, and one with the early stopping patience is equals to 15. So these are the three key main parameters. One is the monitor, which metric to watch for the validation loss is, like validation loss is a standard, but we can change it also. So monitor will tell what you want to watch, patience is how many epochs, and restore base, which is reloads the checkpoint when stop. So we'll build a simple model first, then we will do model A, B, and C. We'll define the three models that we have already discussed, and then we will plot all the three models, and then we will print the summary. So we can see no early 150 epochs, actual 12 epochs and then 25 epochs, and what happens to the accuracy and the best value loss. So early stopping is equals to free regularization. It stops fast and might stop too early. Underfitting risk is there when the patient's value is low. When the patient's value is high, it's more tolerant and find a best minimum value. And restore best weights is equals to true. So we always use this to guess the best epochs and the not last epoch. So it will get us the best epoch, not the last epoch value. Now next is we will do early stopping with the PyTorch. So PyTorch do not have inbuilt early stopping like Keras, so we built it ourselves, a clean reusable. So we have these three tests again. One is for full 150 epoch that we did, one with 5 and 15 patients. So first we will define the early stopping class. It monitors the value loss and stops training if it does not improve. Also saves the best model weights like restore best weights in Keras. So we have defined init function where we will pass the patient's value. We'll define all the variables, and then we will define a call function which will execute, and it will change the counter values, and then we have defined this restore function that will load the best weights back into the model after the training stops. So first we will train the functions with optimal early stopping, where patience is none, that means there is no early stopping, but if there is an integer we will use the early stopping. So for each epoch we will do training, we will compute the train loss, and then we will do the validation plus accuracy, full validation and accuracy, and then we will check the early stopping. If early stopping condition is matched, it will stop, otherwise it will continue. So this is build and train three models. We are building and training the three models, and then we will plot the loss curves and we will see the summary. So we can see here early stopping stopped at 15 epoch. First model A trained with no early stopping. Model B early stopping with 5 patients. It stopped at epoch number 18. Third is model C early stopping with patients 15. So it stopped at epoch 33. So all these three models are trained, and we can see the graphs are plotted, and the best value validation accuracy loss value is more on the early stop, and then the results are almost same. So next is the MC dropout, Monte Carlo dropout using TensorFlow. So normal dropout is off during the inference, but the MC dropout keeps dropout on during the inference too. So it runs the same input n times and get n different predictions, and the spread of those predictions gives the model's uncertainty. So the key trick is here in Keras we call model X and training true instead of model dot predict to keep the dropout active at the inference time. So we will build a model with dropout, and then we will train the model normally, and then we will train with the dropout inference, and we will compute the mean and the uncertainty, and we will predict the final class. And then we will plot for each test sample, and we will see how it works, and then we have this print summary. So we have this trousers and it predicted trouser. We have this trouser, it again predicted trouser. We had this shirt and it predicted it as a pullover. We can see the pullover value is larger, and so it got confused in shirt and pullover. All others it was able to predict correctly, but we can see where it is predict correctly the confidence value is high and uncertainty value is low, but when it predicted wrong, the confidence value was low and the uncertainty value was high. So when the confidence is low and uncertainty high, model is unsure. When the confidence is high and uncertainty is low, the model is sure. So this is how this model works. Now let's see MC dropout with PyTorch, and again we are defining this dropout function. We are training the model. We are doing predictions, and then we are storing it. We are doing inference, and then we are plotting the images with the uncertainty, and we can see it, the prediction results. So ankle boot prediction, ankle boot prediction, pullover, trouser predicted trouser, and everything is predicted correctly, even the shirt is predicted correctly. So everything is predicted here correctly, and that's why it works very well. And this is the main difference in the tensor and PyTorch. How MC dropout is enabled is the main difference. In TensorFlow, we do it with model X train true, and here we do model dot train. So this is the main difference. The next is the weight initializations using the TensorFlow. So we will run it for the 50 epochs. We will build the model, and we'll build a model with different dense layers, and then we will set the configurations, and then we will train all the four. We have defined four configuration. Here is 0 random normal, Xavier Glorod, he is normal, he normal, and all this four we are going to train on all this four, and then we are going to plot and see. So we have all the four here, ABC test. We are plotting the validation accuracy, the training loss. Here only the 0 got stuck and it didn't work because all neurons are same and zero gradient, and therefore no learning. So that's why the weights initialization technique didn't work here. But if we see the same thing with PyTorch, let's see what happens. So in PyTorch, initialization are applied manually after creating the model using torch.nn.init function. This gives more control to Kira's string shortcuts. So first we'll define the base network, no init yet, and then we will apply init function using torch nn.init. So we can see nn.init.zeros, nn.init.normal, nn.init.xavier, nn.init.kaming normal. So everything we are doing using that torch operation, and then we are defining the training function, and then we will train all the four configurations, and we will plot the graph, and let's see how it works now. So again, the 0 1 got stuck and it performed differently from the rest 3 tests, and the rest 3 tests worked very fine, and we can see the results here. So this is the main difference between the PyTorch and TF initializations, how we initialize the weights. So the next section is batch normalization. So batch normalization at each layer inputs to mean 0, standard deviation 1 during the training. This speeds up the training, reduces the sensitivity to initialization, act as a mild regularization, and help with vanishing gradients in the deep network. So the placement is most important here. The batch norm goes between the dense and the activation function. This is the correct order, but sometimes people also use it after the activation, like dense activation and batch norm, but that is a debated one. The best correct order is dense, batch norm, and then activation. So we'll again do the ABC test. A will be the with no batch norm, B will be batch norm after each hidden layer, and C will be batch norm with dropout combined. So we have this model A, model B, and model 3 defined here, and we'll build and compile and train all the three models here, and then we will plot the three panels, and then we will see the comparison of all the models and the summary. So we have this no batch norm, with batch norm, with, and this is with batch norm and the dropout. So the converges also we can see, and we can see the validation accuracy is almost same, the training accuracy is almost same, and the gap is also almost same. So this is the key insight. The batch norm one is faster convergence and smaller training validation gap. For batch norm plus dropout, we use it for the best generalizations, and that's all. Now we will do the batch normalization with the PyTorch. In PyTorch, we use nn.batchnorm 1D and nn.batchnorm 2D for dense and the conv layers. And like dropouts, batch norm behaves differently in model.train and model.evaluation. Let's see how. So first we'll define a three network variants. These are the three network variants that we have defined, and then we will do a generic train function on all the models, and then we will train all the three models. Once the training is done, we will plot the accuracy curves, and then we will plot the converge speed, and then we will see the summary. So we are plotting this graphs, and then we are plotting this converge summary, and we can see this batch norm summary for the PyTorch. So again, it's almost same for all, and this is what we have done. So in the major difference between TensorFlow and PyTorch batch norm is, in TensorFlow the auto mode switching is there, but in PyTorch it's manual training and evaluation we are using, and the way we are using it is different. Here I have given it. The next thing is custom dropouts and the regularization. So we build our own dropout layer and regularizations from scratch, and this shows what Keras does internally under the hood. So let's see how custom dropouts and regularizations are implemented in TensorFlow. So here we are defining our custom dropout layer. Uh, we are creating a random mask of drop, and then we are scaling kept neurons so expected values stay the same. At inference we return as is, and then the second part is custom regularizations L1 plus L2. So we are defining a regularization class here. We are defining the regularizes L1 and L2, and then we are defining the call function where we will call it. So we will build model using both the custom components here, and then we will do part A and B custom versus built-in training. We'll call our custom defined functions, and then we will compare it with the built-in functions, and then we will do the training, and we will plot the comparisons of the custom and the built-in functions. So let's see. Here blue is the custom blue is the custom dropout and regularization, while the yellow dotted is the built-in, and we can see the built-in has slightly higher validation accuracy than the custom one. Both should be nearly identical, and that's why we can see it in the graph also. The next is we'll do built custom dropout and regularization using PyTorch. So again we are defining here the dropout function using PyTorch, and then we are defining the custom regularization function here using PyTorch, where we are using sum of squared weights method, and then we are defining the built-in model with components, and then we are training with the loop, and then we are using custom and built-in test, and then once that is done we will plot it and see the difference. So here is the custom versus built-in graph, and we can see it's almost similar, both are nearly identical, and that's what we can see here. Now the next is the callbacks and the tensor boards in the TensorFlow. So Keras callbacks run automatically at specifically training events. We demo four most useful ones: model checkpoint, early stopping, reduce, LR on plateau, and the tensor board. So there are different steps in it. So let's see. Step 1 is building a simple model. Then we will define all the callbacks, save the best model weights automatically, stop early, reduce learning rate, and then tensor board. All the four we have defined. We will train all the callbacks active, and then we will plot the training curves, and we'll see how it works. So these are the accuracy of the callbacks. We can see we have printed the best model, we have printed the tensor board logs, we have the final LR, we have the epochs run. Early stopping, we stopped only on the 34th epoch. So all callbacks summary we can see here. Now let's see all the same callbacks, how can we implement it with the PyTorch manually. So again here we will define a simple network, and then we will train with the callbacks. So we have here the reduce LOR plateau callback, the TensorFlow callback, the checkpoint variable callback. We'll train and validate all the callbacks. First one will save the best model, second will step scheduler for LR changed, third is the tensor board logging, All this we are doing, and then we are running and plotting it. So this is what we are doing here, and we can see the outputs again here for the PyTorch. So the same thing we have done with the PyTorch and TensorFlow. The next is the Keras tuner. So Keras tuner automatically searches for the best hyperparameter instead of manually trying to combine. It does it for us. So first is installing Keras tuner. Step 2 is defining model build function for the tuner. So we have defined this function. It will define function for the tuner. So here we are defining the sequence and then the model dot compile. Once that is done, we will create a tuner with objective is maximize the well accuracy and maximum uh, trials as 8, so it will try 8 random combinations. Then it will print the search summary, and then we will run the search. So we will print the summary, and we will see how we are getting the best hyperparameters. We'll again do the A/B testing with tuned and the default model to see how the tuned model work differently from the default model, and we will plot a comparison graph. So we can see starting hyperparameter, it run this much, this is the dropout, everything it is printed. Best hyperparameter are found when the units are 128, the dropout value is 0.2, and LR is this. So this is the best hyperparameter, and we can see the graph. The green one is the tuned and the red one is the default, and the tuned model has better accuracy than the default model, that is around 0.019 improvement we can see. The next section is Keras data augmentation. So in Keras data augmentation, we'll first reshape the image, and augmentation will set the pipeline. We will visualize the original versus the augmented data. First we will build a simple NNN, and then we will build a model with no augmentation, another model with the augmentation with the data, and then we will plot the we will test on both the datas and both the test A and B, and then we will plot A and B test, and we'll see. So we can see this is our output, and original versus the augmented. These are the original photos, and below are the augmented photos, and both models are trained, and we can see the accuracy is more with no augmented, and the overfitting gap is almost same for all both. Now the next is we'll install and verify Ogly. So here we are doing that, and then we will do image augmentation using Ogly. So this is the helper functions that will convert array to RGB and then RGB to 784 dimension arrays. So this will do several times in upcoming code. So let's see. Now first is we'll show these 6 transformations: original, brightness, contrast, blur, flip, all those things. And here we are defining the built augment data set, and once the augment data set is built, we will define the classifications, and then we will train without augmentation, and then we will train with augmentation, Ogly augmentation. And once that is done, we will plot the output. So let's see the output. This is the original data, and this is the printed data, one with the augmentation and one with the without augmentation. We can see image classification with Ogly versus without Ogly, and the output says the validation accuracy is better with Ogly, and it gives better generalization also. Next section is the text augmentation. So in the text augmentation, we will do 4 types of augmentation, that is word swap, word delete, word insert, character keyboard. So we have these 4 sentences. We will define the 4 augmenters, and then we will show the augmented versions of each. And then we will have the second data set, and then we will try without augmentation, with augmentation, and then we will plot the augmentation examples visually. So this is what we have. This was our original sentence, and then we are doing word swap, delete, all the same functionalities we are doing with the all the 4 exam sentences. Once that is done, we can see the text classification, it's same accuracy for both. So this is how we use the text augmentation. Next is the time series augmentation. For time series augmentation, we will do jitter, scaling, time wrap, all these functionalities on the time signal. So we have this time series defined here. We will define four augmenter functions, that is the jitter, scaling, time wrap, and the window crop. Once that is done, we will visualize all the four augmentations, and after the visualization we will define A B classification with augmentation, and we will do it. We will augment the training data and then we will run the classifiers and we'll see. So this is our original time series. This one is with jitter, this one is for scaling. We can see the time wrap, it's almost overlaps. We can see the window crop also. We can see all the augmentations in one graph. So this is how we do time series augmentation. For the tabular data augmentation, we have Gaussian noise, feature dropout, mixer, smart style, all this kind of techniques. And first we will create a toy tabular data set. Once that is done, we will split it into training and test, and we will define the four tabular functions. Once the define is done, we will visualize the augment features, and once visualization is done, we will do A B classification test on it, one with no augmentation, one with Gaussian noise, one with mix up, one with smart style, and then we will plot the results. So we can see the original data, that is no augmentation, then Gaussian noise augmentation, mixing up samples, and then smart style synthetic, and we can see the tabular augmentation comparison where the no augmentation or smart are almost similar. And the next is the speech augmentation. So in this we are taking speech as a signal. So we are creating a synthetic audio signal and we are doing all these techniques, adding noise, time shift, speed change, volume, scale change, all these things we will do. So we have defined for each speech augmentation functions, that is add, noise, time shift, speech change, all the functions we have defined, and we'll visualize all the augmentations, and then we will do A B classification test on that noise, and then we will print it. So here we have this original waveform, this is adding noise to it, this is time shift, this is speed change. You can see the wavelength there, it has been decreased, the volume, scale, the height has decreased of the signals. So all these functions we are doing on the speech. So this is what we can see. So we can see with noise augmentation, we can see the accuracy is increased as compared to no augmentation. And in the next section we will do the document image augmentation. So the techniques we'll do is brightness, blur, rotate, noise, all these techniques we'll do. We have defined this helper function that we have seen earlier. Now we have defined this specific augmentations that we are going to perform. We'll visualize all four document samples first, and then we will do the classification, and then we will do the training of the test samples, and then we will do the final output. And we can see this is our original data, this is the brightness, this is blurred, this is rotated, all the functions are applied on all the data set. And we can see the difference between no augmentation and document augmentation, and there is a slight difference of the accuracy. And yeah, that's all for this assignment. We have completed all the sections and we can of part 1, and you can see the summary in this summary section with all the results. That's all for this video. Thank you so much.